Okay, this is our last video on section 11.2. And this is one other type of chi-squared test, and this is chi-squared goodness of fit. So they're abbreviated GOF. So similar to what we did last section, but just a totally different kind of test. So last time we used chi-squared to do a test for independence, and this time we're going to test how good of a fit is a particular distribution for some particular scenario. So the example we're going to look at is section 11.2, number 3. So number 3 talks about retailers of collectible postage stamps often buy their stamps in large quantities by weight at auctions. The prices the retailers are willing to pay depends on how old the postage stamps are. Many collectible postage stamps at auctions are described by the proportions of stamps issued at various periods in the past. Generally, the older the stamps are, the higher the value. At one particular auction, a lot of collectible stamps is advertised to have the age distribution given in the table provided, which I'm going to draw for you in just a minute. A retail buyer took a sample of 73 stamps, write that on here really quick, from the lot and sorted them by age. The results are given in the table provided, and we want to test at 5% level of significance whether there is sufficient evidence in the data to conclude that the age distribution of the lot is different from what was claimed by the seller. So here is our distribution given in the table in the book. They give you a year, and that was before 1940 to 1959, 1960 to 1979, and after 1979. We have our rows, so this is very similar. You have still a column of sort of table of things, and this is the claimed values, and this is the actual observed that we saw. So the claimed distribution is 0.1, 0.25, 0.45, and 0.2. So this is the proportions, and then these are your counts. So in the sample that they actually took, they got 6 before 1940, 15 between 40 and 59, 30, and 22. So this is how the problem starts. And what we have to do is create a test to decide if this distribution right here, the one that's given in the problem, is the actual distribution, or if there's something off about that. And so those are our null hypothesis and our alternative hypotheses. So I'm going to go ahead and write these hypotheses right here, because the other thing I need to do involves this table, so I'm going to try to stay on this slide as much as I can. But your null hypothesis in a goodness of fit test is the distribution is as given. And sometimes I like to write that out, but otherwise it's right here on this table, so I can probably see it. And your alternative hypothesis is the distribution of stamps differs from given. So you can write something along those lines. You're really testing to see, is the distribution that's claimed the correct one, or is the distribution of stamps something different from what is given? Those are always your hypotheses in a goodness of fit test. So if you have a goodness of fit test, this is your H0 and this is your HA. There aren't anything different. So it's very similar to the one we did for independence. You can also write an equation here if you really wanted. You could do like P 1940 equals 0.1, P 40 to 59 equals 0.25, P sub like 60 to 79 equals 0.45, and you could do some stuff with P's. And we'll talk about some of those examples in class, but this is the general way that you would write out these hypotheses. So before I continue, the other thing we're going to need in these problems are what are known as the expected counts, and I want to go ahead and put that in our table here. Just like we had to do expected and observed for the independence test, we're going to do the same thing here. So the expected counts are really just, you take your n times your observed distribution. So this is just going to be 73 times 0.1. That's our n from over here. 0.1 is how many we're supposed to get, so we're going to get 7.3 here as our expected. And if you do that all the way down, you're just taking 73 times each of these things. So 73 times 0.25 would give you 18.25, 73 times 0.45 is 32.85, and 73 times 0.2 is 14.6. So just as a reminder, your expecteds are just n times your proportion for that particular row and column. Okay, so now we did step 1, the hypotheses we have on the previous page, so we're good to go there. Step 2 is a conditions check. The first condition is that the assumed distribution holds. And we're going to assume that and move on. And the second condition to check is that all the observed are greater than or equal to 5. And in this case, we're also good there. So if you look back at the observed counts, I think the lowest one is 6, so we're good to go there. Now it's time to calculate that chi-squared. Remember, it's just the sum of your O minus E squared divided by E. So in this problem, that's going to be 6 minus 7.3 squared divided by 7.3 plus 15 minus 18.25 squared divided by 18.25 plus 30 minus 32.85 squared over 32.85. I'm probably going to run out of room. The last one is 22 minus 14.6 squared over 14.6. So you'll do all those calculations. You want to practice that with a calculator. I got 4.808. And that is my chi-square test statistic. That's the third step of the calculation. Step 4, remember, is to calculate a p-value. So for this one, we need chi-squared, remember, and we need degrees of freedom. And in this case, the degrees of freedom is the sort of number of categories minus 1. So in this case, we had 4 categories, and we subtract 1, so we get a degrees of freedom of 3. Another way to think about it is the number of terms in your chi-squared statistic minus 1. That's another way to remember it. So the number of categories minus 1, 4 minus 1 is 3. That's our degrees of freedom. So now if you go to your chi-squared chart in the back of the book, and we go down degrees of freedom is 3, and we look at the first number in that chart. I'm going to flip now in the back of my book. You can see that. If we look at the very first number for chi-squared 3 degrees of freedom, I get 6.251 for 0.1, and then I get 0.05, I get 7.815. So our test statistic was 4.8 something, so that actually falls here to the left of 0.1. So remember, that tells us that the p-value is going to be greater than 0.1. We don't know what it's going to be exactly. You cannot get exact p here. But it does tell us a pretty good idea of what we're going to get, and we know, for instance, here the p-value is going to be greater than 0.1. So in step 5, we know the p-value, which is going to be greater than 0.1, is certainly going to be greater than alpha, which is 0.05 for this problem. So that would tell us that we failed to reject H naught. And so your conclusion is there is not sufficient statistical evidence to conclude the distribution differs of stamps differs from the given distribution. And that is your chi-square test for goodness of fit. We will look at one more example in class on Wednesday, but pretty much this is the process.